Welcome to complex roots in theory. So recall if if ay double prime plus by prime plus cy equals 0 has characteristic equation ar squared plus br plus c equals 0 with complex conjugate roots then we have complex conjugate roots r equals u plus or minus iv. Then we have complex valued solutions. Y equals e to the u plus iv times t or times x for our y1, and y2 equals e to the u minus iv times t. But again, these are complex valued solutions. So the question is, how do we get real valued solutions? To do this, we are going to use a formula called Euler's formula. Euler's formula states if we have e to the I times theta, this is equivalent to cosine of theta plus I sine of theta. So this is Euler's formula. Why is this true? We can go ahead and use the series expansions of each of these. So e to the x is given by the series from n equals 0 to infinity of 1 over n factorial times x to the m. So if we do e to the I theta, we would be looking at the sum from n equals 0 to infinity of 1 over n factorial times I times theta to the n, or e to the I theta is equal to the sum from n equals 0 to infinity of I to the n times 1 over n factorial times theta to the n. So we're going to use a trick here for I. So note, I to the 0th is just 1. I to the first power is I squared is -1. I cubed is -I. And then I to the 4th, we just loop right back to the beginning. So you can see when we have even exponents, we will always land on a real value. And when we have odd exponents, we land on an imaginary value. So we're going to split this into two pieces. We're going to have the sum from k equals 0 to infinity. And then we're going to look at evens, so 2k. So we'll have I to the 2k times 1 over 2k factorial times theta to the 2k. And then we'll split again going from k equals 0 to infinity of I to the 2k plus 1 times 1 over 2k plus 1 factorial times theta to the 2k plus 1. This first piece here actually becomes just -1 raised to the k, since I squared is -1. And so we're looking at the sum from k equals 0 to infinity of -1 to the k times 1 over 2k factorial theta to the 2k. The second piece, we can factor out an I from our I to the 2k plus 1. We're just left with I to the 2k inside. And this actually winds up being, again, the sum from k equals 0 to infinity of -1 to the k. My screen's not updating. One moment. So we pulled out an I that was the plus 1 from the exponent. I to the 2k again becomes -1 to the k. Oops, sorry about that. Times 1 over 2k plus 1 factorial times theta to the 2k plus 1. Now, you may or may not remember your series from Calc 2. But this first piece here is actually the series, Maclaurin series for cosine of theta. And this second piece here is actually the series for sine of theta. So this is equal to cosine of theta plus I times sine of theta. So this is extremely useful for us. We now have the e to the I theta is just cosine theta plus I sine theta. And then we can expand this. So expanding this, or expanding upon this, if we have e to the u plus ib times t, this is e to the u times t plus I times v times t, or e to the u times t times e to the I vt. And then if we use Euler's formula, this is e to the ut times cosine of vt plus I sine of vt. So if we have a solution in the form e to the u plus iv all times t in that exponent, we can split it out sort of into the real part component and the imaginary component. So from here, we now are going to utilize a very useful fact, which is if complex solution y of t equals, or if, we'll go this, if y of t equals some function u of t plus I v of t, where u of t is real valued and v of t is real valued. So we've broken our function into the real and imaginary components. If this is a solution to our differential equation, on open interval AB, then the real and imaginary components also are. So then U of t and V of t are also solutions. This is extremely useful. So for our solution, y equals e to the u plus iv times t. We have y is equal to u to the u times t times, in parentheses, cosine of vt plus I sine of vt. And this is equal to e to the ut cosine of vt plus I times e to the ut sine of vt. Here's our real component and our imaginary component. Both of those are solutions. We get that y1 equals e to the ut cosine of vt, and y2 equals e to the ut sine of vt are both solutions. So we're using a mix of Euler's formula and the fact that the real component and imaginary component of our solution are also solutions to the same differential equation. So now what we need to check here is, do these solutions form a fundamental set? If so, then we now know how to solve any constant coefficient second order linear differential equation, homogeneous, with characteristic equation with imaginary roots. So let's take our Wronskian. So before we actually do that, we have y1 is e to the ut cosine of vt. So y1 prime, we're going to have to do product rule. We would have this is equal to u e to the ut cosine of vt plus v, or minus, sorry, minus v e to the ut sine of vt. As an update. Similarly, we had y2 equals e to the ut sine of vt. So we would have y2 prime is u e to the ut sine of vt plus v e to the ut cosine of vt. So our Wronskian, we are looking at the Wronskian of y1 and y2. This is equal to y1 times y2 prime minus y1 prime times y2. So we are looking at e to the ut cosine of vt times u e to the ut sine of vt plus v e to the ut cosine of vt. And then from that, we are subtracting e to the ut sine of vt times u e to the ut cosine of vt minus v e to the ut sine of vt. this becomes u e to the 2ut cosine of vt sine of vt plus v e to the 2ut cosine squared of vt minus u e to the 2ut cosine of vt sine of vt plus v e to the 2ut sine squared of vt. So that, oh, again, I'm not updating. I apologize for all of the pauses and updating. Okay, so now everything's written out. The first term in each of my rows just cancels out. So these will cancel each other out. And then the rest we're left with v e to the 2ut times cosine squared of vt plus sine squared of vt. Cosine squared plus sine squared is just 1. So we have our Wronskian as v e to the 2ut. Now e to the 2ut is never 0. And v in this case is never 0. Otherwise, our roots are equals u plus or minus iv would not be complex, and would not be in this case. So we get then that our Wronskian of y1, y2 is not equal to 0. And therefore, y1 equaling e to the ut cosine of vt and y2 equaling e to the ut sine of vt form a fundamental set of solutions. So in the next video, we will do a little practice actually solving for these solutions.